highest power of t you see in that quadratic function? 2. So it's a quadratic. Let's ask some questions about it. So the first prompt is when, well, let's read the setup. Rugby League high jump world record is currently held by Mandarin of the Orangers. Mandarin leaves the ramp with an initial velocity of 285 centimeters per second. According to physics, the height as a function of time is now given by 285 centimeters per second. So a term coming from velocity times time minus 5 meters per second squared times time squared. So like the standard thing that comes from acceleration due to gravity. When will Mandarin achieve their maximum height? So, let's see, that sounds like it's asking for a maximum. So the vortex formula will be relevant. It's asking for the when, so we want to know the time that it happens. And time is the input, so we want the input that corresponds to the vortex. That's good, that's exactly what the vortex formula tells us. And in a perfect world, I just now say you all have some people around you that you might be able to collaborate with. Do you think you can do it? That being said, I'm going to make a call for if someone feels like they're absolutely stuck and doesn't know where to begin and would like me to say something else beforehand. Cool. Yeah, then So the thing that makes this problem different from the stuff that we did last time is just the units, right? That's all. So let's check this first. So if the units are all consistent, we can probably ignore the units. Are the units all consistent? Cool, so we've got to fix that first. What is the inconsistency in units in this problem? One's in meters, one's in centimeters? Cool, so I guess we now need to make a choice. Do we walk only in meters or do we walk only in centimeters? And it's a choice. Only in meters? Only in centimeters. I think centimeters have a few more hands. Let's convert everything to centimeters. If you want to walk in meters, that's fine. So let's convert everything into centimeters. And this is the only place where I see meters, so let's walk on that first. 5 meters per second squared. So the standard way to convert units is to think about multiplying by 1 in the right way. And I want to multiply by 1 in a way that lets me get rid of meters and introduce centimeters. How many centimeters to 1 meter? 100. It's in the name, right? If you know a little bit of Latin, you know that centa corresponds to 100. Same thing as why a percent is per 100. So that means that this thing, 100 centimeters divided by 1 meter, is 1. So I'm going to multiply 5 meters per second squared by 1. But it's a very particular one. It's a 1 that lets me cancel those meters and get centimeters into play. So what does that become? 500. And I'm going to keep the units here for now. I'll get rid of them in a second. All right, if I make that replacement, are the units now all consistent? Nice. So that means I will now forget them. So the height as a function of time is 285t minus 500t squared, t in seconds, height in centimeters. All right, with that change now made, let's remember what the goal is. I want to know what time corresponds to a maximum height. Does that look doable? Does anyone feel like it does not look doable? Cool, then do it. Tell me what the time is that this thing is at its maximum height, and then tell me its maximum height.
So we can just set this one's t squared, and it's usually so we have this one x squared has 5x. And you can solve the other one because we know that a is equal to a and b is equal to b over 2a, and we have both of those things solved, and then c is equal to c minus b squared over 1.
I like that. So do that and see what answer you get. You'll get the same answer, and then we'll talk through the way that I'm encouraging that it should work.
This was just what my calculator is. That would be like some buddies.
Oh,
So actually, I have to do this.
You would do just well, I have other questions here that this one would be this square bracket. Yeah, that makes sense. It's just in the wrong way. Yeah.
Yes.
I mean, that's not that crazy. It's like 3
Well, I mean, yeah, it's not that crazy.
And like, the numbers in the problem have like 3 digits, so.
Right.
Alright. Come together and just touch base. At what time is the maximum height achieved? .285 seconds. Do I hear a second? Nice. So the max height occurs at time equals 0.285 seconds. It's nice to put the 0 before the decimal point just for readability. Otherwise the decimal point gets lost, then you think it's 285 seconds. At least I do. Groovy. All right, so what is the maximum height that this miracle achieves? 40.6125 centimeters, I guess?
Yeah.
Do I hear a second? Cool. How'd you get it?
Put 0.285 into the age.
Yeah, cool. We know the time value that corresponds to the max, just plug in that time value. Max height equals 40 point, and I didn't write them down when you said them, and I didn't do them on my own.
6125.
6125 centimeters. All right. All right, so let's talk through, like, do people want to see the max height discussed at all? Cool, yeah, let's do it. So as soon as you know, well, maybe I'll ask Bill. Before that, should we talk through how to find the time value? Is there a call for that? Cool. All right, so let's think about this function. If you want to graph it, don't graph it, but if you want to graph it, would be an upward opening parabola or downward opening? Down, because that 500 is negative. So, downward opening parabola, so the vortex maximizes. We need to find the vortex. Last time we got a formula for the vortex. The formula for the vortex says that the vortex will occur at an input value of b over 2a. It says x here, but x is just whatever the input value is. So here the input value is t. So vortex at t equals negative b, so negative 285 over 2a, so 2 times negative 500. That feel pretty okay so far? Does that indeed simplify down to 0.285? Yeah. So I heard one interesting idea that someone mentioned for like finding the time value of the vortex. And it agrees geometrically. It's something that makes sense. You know that like the flight of this marble, if you want to plot it, should be something like that. It sure looks like that vortex is exactly halfway between those two x-intercepts. The t value of the vortex is in between those two t-intercepts.
Why is it negative 2 as
Because the vortex formula says negative b over 2a.
Oh, okay.
Let's finish up the problem though, because the negative sign will go away.
Right.
The 500 is also negative, so the double negative will cancel. And you'll get 285 over 1,000. Yeah, that's 0.285. Now you have to remember it's in seconds. So how many people went and found the two x-intercepts of this thing first? Ah, okay, cool. Then you could have. It would be harder to do so, because the quadratic formula is more complicated than the vortex formula. If you found the two x-intercepts, the vortex is exactly halfway between them, so you could do that if you wanted to. You'd get the same answer. The reason I mention is I heard some people discussing it, and I wanted to bring it up. It's correct. It's more computationally intensive. How many people even just straight up completed the square? Cool. Also not wrong. Did you use the completing the square formula, or did you do it by hand?
The completing square formula.
Oh, cool. Yeah. And notice the completing the square formula. There's the b over 2a. Oh, so does that mean you also just recorded this number as the height at the vortex? Okay. I guess if you do it that way, maybe it saves you some computation. Otherwise, you have to plug that number into this formula, which maybe takes some more too. Cool. People feeling pretty happy? Feel pretty good about optimization? All right. Let's change topic a little bit. What if instead of asking what the maximum height this thing achieves is, what if I just told you the previous height world record is 38 centimeters, and just asked you, is there a time at which this Merkel's flight exceeds that height? Do you think you could? Yeah, I guess one thing you'd do is you'd say, well, I just need to set them equal and see if it has a solution. In fact, you could see how long it's above that height threshold by solving an inequality. So let's change topic a little bit. Let's solve quadratic inequalities. I'm not going to actually do that. I have like a different problem in mind. So today's goal, how to solve stuff like that. And ultimately, so what I'll get to at the bottom of this page is more or less an algorithm, a plan of attack that'll solve this. In order to set up what that algorithm is, I think I want to do something totally wrong first. Well, wrong first, and then we'll try to salvage it. So here is a setup for a problem. Dennis Mitchell has snuck into the backyard of one Mr. Wilson and is playing toss with a ball. Each toss, oh, that H should be capitalized. It's the start of a sentence. Imparts the ball an initial velocity of 15 meters per second. The flight of the ball is now modeled by like the standard thing that comes from like gravity, right? There'll be, if you want to be really precise from the physics, you'll get like negative 4.98, but I'm going to round that right to 5 meters per second. Suppress the units or keep the units? Suppress units? Keep units. Okay. Negative 5t squared plus something coming from the initial velocity. The only danger in like throwing the units out is you need to make sure you're being consistent with units. That negative 5 only walks if you're walking in meters per second. Is this walking in distance of meters? Time in seconds? Okay, good, then you don't need to worry. Mr. Wilson is inside on the second floor reading a newspaper. When the ball exceeds a height of 7 meters, it will enter into Mr. Wilson's field of vision. For what times is the ball within Mr. Wilson's field of vision? So that's like set up as a problem, right? It's like obviously made up, but you know, there are laws, which is nice. What inequality do we need to solve if we want to like know the answer to this? Yeah.
Negative 5t squared plus 15t squared is 7.
Yeah. 5t squared t bigger than 7. Because I want to know when is the height of the ball bigger than 7 meters, because I want to know when it's in Mr. Wilson's field of vision. Being in the field of vision is the same as being above 7 meters. People would want to interpret this problem as bigger than or equal to 7 instead. That would be fine, I think, if you did. Right? Like, what difference does it make? Like, if it's in or out of the field of vision at that threshold moment? I don't know. Anyway, let's use the following flawed strategy. So that looks like the numbers are complicated, so I don't expect like factoring to help me. So instead, what I'll think about is the quadratic formula. Or like that's the cop-out strategy when factoring doesn't work. You could complete the square and then solve directly, but I think that's more computationally intensive. Let's use the quadratic formula. So to set that up, I guess I need everything on the same side. Negative 15t squared plus 5t minus 7 bigger than 0. And the quadratic formula is going to produce like two solutions. So let's just like find them. And this is the step where something wrong is going to happen. And we'll talk about what's wrong about it once we're at the bottom of the page. So the quadratic formula says that this should have a solution, t bigger than, and now I'll use the quadratic formula, negative b plus or minus the square root, b is 15, b is 5. No, I'm losing things left and right. You can correct me when I make a mistake. I mean, I do it a lot. All right, negative b, negative 15 plus or minus the square root of b squared minus 4 times 5, 4 times a, times c, all over 2 times a. And like, I don't feel like doing the work of using the quadratic formula myself. I will if someone like really demands. But in fact, in a perfect world, I'd say y'all like computing machines, most of you. Tell me what that is. I don't want to do the work on my own. Unless someone wants me to. Does anyone actually want me to? Cool. Oh, and maybe just while people are using calculators, those of you who have like cell phone calculators, out. It's fine right now, but I'm obviously not going to let that fly on the exam. As a reminder, the math department office on the 5th floor will let you check out a calculator. Just show up there with your student ID, like 10 minutes before class probably would be a good idea. Get in there, show them your ID, they'll take the ID from you and then they'll hand you a calculator. Doesn't even need to be your student ID if you're like the type of person who uses your student ID as a bookmark and so loses your student ID all the time. Like anything that they're convinced is valuable enough, you'll come back for it. Cool. So what are those time values about? Give me, say, up to the 10th of a second or something. 100th of a second, 100th of a second.
I got 0.57 degrees add, and then 2.422 subtract.
So 0.578 seconds and 2.422.
422.
And those are both in seconds. So it sure looks like, do I hear a second or any disagreement either way? Do I hear agreement? Do I hear any disagreement? Do I hear a call that I should like do the work? Oh, I did want to point out one thing. So how many people like took their calculator and tried to type in just like that verbatim? Cool, it's fine if you did. You probably could have made your life a little bit easier because you can do some of the steps on your own. Right, like what's 2 times 5? Yeah, I guess what I should have asked is what's 2 times negative 5. So negative 10. So you could have replaced the denominator with negative 10. There's a double negative in the numerator. Those two negatives will cancel. You know what 4 times 5 is? It's 20. Oh, 20 is easy to multiply by 7. 2 times 7 is 14, so that whole thing is like 140. 15 squared is maybe a bit much. but after making those replacements, there's less to type. Anyway, so we see the 2 times, and let's like draw a picture of what this answer is in order to see that like something goofy is going on. So the first statement says that at a time value of about 0.578 seconds, it enters the field division and then stays in the field division forever. The other one says that at a time value of 2.422, because that's a t is bigger than, it enters the field division and then stays into that field division forever. That seems wrong, right? Like this says that the ball goes up, it enters the field division, then it enters the field division again, and then it never leaves. That's obviously nonsense. So like, I don't know. How would you want, like, fundamentally what went wrong is the quadratic formula solves equalities, not inequalities. And we used it to solve an inequality, and it didn't have to do with those inequality signs. We just like did something. So how would you want to fix this? Just intuitively, what do you think the answer to this should be? Yeah.
It's meant to be like, in the field division between 0.578 and like 2.422.
That certainly would be intuitive, because you know that when you throw a ball, it goes up, it hits a maximum, and then it comes back down. So I bet the first one is it entering the field division, the second one is it leaving. But the quadratic formula doesn't know that. You have to think about that independently. So I sure think about 0.578 to 2.422 is the solution to the inequality. But in order to see that, you have to think independently about what the solution should look like. So, like, we made it to an answer, but there was like a hand wavy step at the end where we like had to figure out how to fix this quadratic formula issue. So here's how I'm going to propose a restructuring of how you think about solving quadratic inequalities. So whenever you see a quadratic inequality, the first thing that I'll suggest you do is you solve equality. So this would be like determining when the ball is at exactly 7 meters, because that's when it's either entering or leaving Mr. Wilson's field division. So let's solve negative 5t squared plus 15t is equal to 7. And in fact, have we already done the work to solve that? Yeah, it's like all that quadratic formula stuff. So that's at t about 0.578 seconds or 2.422 seconds. Those should be t values, but that's just fine. All right, so those are the moments when the ball either enters or leaves the field division. So we have to think about now, like, is it entering or leaving the field division at each one of those times? And we know what the graph of the height should look like. If there's time and there's height, we see there will be these 2 times when the ball will hit a height of 7 meters. There's the first one at 0.578. This next one at 2.422. It looks like during the time in between those two, the height is above a height of 7 meters. So what's the procedure that actually told us the solution? The quadratic formula gave us the endpoints, and then graphing told us that the solution is the inputs that are between. So there's like 2 steps. Find the endpoints by solving equality. Use the quadratic formula, maybe you can factor. Step 2, figure out one of the intervals with those endpoints is the solution. And from there, I think it's just like, do some examples. Visible in between by looking at that graph. So that seems to be negative 0.578 seconds to 2.422 seconds. Oops. All right. So what's on this next page is just a ton of examples. I've stripped away all of the flavor. This is just now solve an inequality. And let's talk through at least one together, and then we'll see what we want to do with the rest. So here's an inequality. F of x equals x squared plus 4x minus 12. Let's determine the x values that result in f of x being bigger than or equal to 0. That is, solve the inequality x squared plus 4x minus 12 greater than or equal to 0. So there are two steps. Step 1, solve the equality. Step 2, do something to figure out what are the intervals bounded by the solutions you found. Solve the inequality. So, step 1, solve the equality. Does that look like an equality you know how to solve? Cool. Do people want me to be the one to do it? Okay, then I won't, because that doesn't do me any good anyway. Go ahead then and solve that equation. Solve this. Once you have it solved, compare with whoever is next to you. Maybe you have to turn around to do that, I don't know. And maybe even compare the technique you used. Is there like 3 natural ways that I could think of to solve this? And solving this quadratic equation is intended to not require a calculator. So, cool. Let's hear on that. What are the input values that solve that equation? I saw some right answers written, and I didn't see any wrong answers written. Yeah.
A negative 6 and 2.
I hear a negative 6 into 2. Do I hear a second? Nice. Quadratic formula or factoring?
Factoring.
Factoring? Anyone else choose the factoring word? Anyone go for quadratic formula? Cool. Those of you who did the quadratic formula, it's not wrong, but I think like some numbers got big if you did that. Not that that's bad, but maybe it's hard to recognize when it's a big number under a square root. Negative 2 and 6 or negative 6 and 2? Negative 6, positive 2. All right. So now let's solve the inequality. And I'll propose 2 different strategies here. One of them will be more robust and apply in more circumstances. The other one will be easier. So let's use the one that's more robust first. Let's think about a number line. There's like a number line. I know that at negative 6 and 2, this function will like cross the x-axis if I want to graph it. That means that negative 6 and 2 are like the end points of the intervals that solve the inequality. That means that for each of the intervals with these endpoints, I just need to plug in one sample value, and that one sample value will tell me the behavior over the whole interval. So, if I'm going to determine whether the interval from negative infinity to 6 is part of the solution, I just need to plug in an input that's less than negative 6. Give me an input less than negative 6. Negative 10. Negative 7 would walk. Negative 100 would walk. I'll use negative 7 for now. It doesn't matter which one you use. That was the first one I heard. So let's plug in x equals -7. So what do I get then? I square it first and the negative sign goes away. So I get 49. -7 times 4 will be -28 minus 12. And all I care about is that positive or negative? And if I can answer it right now, then I'm done. If not, then I have to keep walking. Is it obviously positive or negative? Positive? Cool. 49 wins. Like you're subtracting some stuff, but you're subtracting 30. 49 is bigger than 30. So it works out to be 19, but I don't need to know that. I just need to know it's bigger than 0. Does bigger than 0 make me happy or sad? That's vague. Does it solve the inequality? It satisfies the inequality? So that means everything from -6 on to infinity is included. So the solution is going to include the interval from -infinity to -6. What's an input between -6 and 2? 0. Plug in x equals 0. Do you get something that satisfies the inequality? I hear a no. And in fact, 0 is a good choice. 0 is very easy to plug into a function like this. You just read off the constant term. Plug in now an input that is bigger than 2. Give me an input bigger than 2. 3. 3 will walk. Use 3 if you want. Because it's useful to think about plugging in extreme values sometimes, I'm going to instead imagine that I'm plugging in 1,000. It's like a 3-digit positive number. And here's the reason that I want to do that. If you take 1,000 and you square it, you get like a 6-digit number, 6 zeros at the end, so 1,000,000. Plus another 4,000, so that's still basically like 1,000,000. And then you subtract 12. Yeah, it's basically 1,000,000. It's positive. On the other hand, you can plug in 3 and get also a positive. So that means all of these will be included as well. So looks like the answer is the interval from -infinity to 6, together with the interval from 2 to infinity. And you'll notice I haven't decorated endpoints. How do I decide whether -6 and 2 should be included or excluded? It's a less than or equal to, so
You can include it because it tells you that it's less, you want to find out what it's less than or.
nice. I have a less than or equal to. Oftentimes when you have a less than or equal to, you want to include the endpoints. And in this case, you definitely do. Because where did those endpoints come from? They came from setting this equal to 0. So I know when I plug in x equals -6, I'll get this thing to be equal 0. 0 is bigger than or equal to 0. Cool. That feel pretty good? So the only downside here is like there's some like computationally expensive steps. You had to plug in like 3 extra sample values. Here's a way that's less robust in that I'm going to use the fact that this is a quadratic. But it is a quadratic, so that's fine. In fact, the function that I'm graphing, if I were to graph it, would it be upward opening or downward opening parabola? Upward opening. So the graph of this thing will be an upward opening parabola that has an intercept at -6, 0, and an intercept at 2, 0. It's upward opening, so the graph will look something like this. People agree? All right. So if I take an input to the left of -6, is that y value bigger than or equal to 0? Nice. That tells me all of these should be included. And notice, I could do that without literally plugging in an input. The graph told me enough information. If I take an input between -6 and 2, do I get a positive output? No, it is below the y-axis, so all of these will be excluded. If I take an input bigger than 2, yeah, those y values are positive, so those will be included. So again, it looks like negative infinity to negative 6 together with 2 to infinity. So, what's the philosophy? If you want to solve a quadratic inequality, start by solving the equality. That's where all the hard work actually is. Once you solve the equality, then either check some sample points, one for each possible interval, draw a number line and check all the intervals that these endpoints point the interval into, or draw a graph. And because I have a slightly limited amount of time left, I'm going to skip this next example in order to demonstrate some weirdness that can happen. And I think I even want to change this example. I'm going to place that with bigger than or equal to 0 so I see something interesting happening. And then at the end I'll change it back to see if that changes the answer. So let's try to solve that thing bigger than or equal to 0. So step 1, set it equal to 0 and solve. In the interest of time, maybe I'll talk through it, but you might have yours done before I do. In fact, how many people have already set it equal to 0 and solved? Cool, what'd you get?
-6 and -12.
For this one? I don't think that should.
Oh, I just factored it. I got my X values.
Okay, let's go through it. If I remember right, something will go wrong. Let's go through it. I don't think it factors. So I'm going to use the quadratic formula, getting x equals negative b
Oh, wait.
plus or minus the square root. You found an error?
Yeah, I did.
All right. All right, so there's the quadratic formula. And we could try to walk it all out, but I'm going to focus my attention right now on just what's underneath that square root. What can you tell me about what's underneath that square root? A negative. Right, the minus term is definitely bigger than 16 without even having to compute it. So, this has a negative under the square root sign. This has no real solutions. It does have complex solutions. But whenever you're solving an inequality, complex numbers don't believe in inequalities at all. You can't ask if one complex number is bigger than another. So there are no real solutions to equality. So how many people would just now want to say there are no solutions to the inequality? Oh, that's good. Yeah.
There are none that are equal to 0 because it's above the x-axis.
Nice. Let's draw a picture. I think this thing will always be above the x-axis. And let's see that. I guess there are two good ways to see it. It definitely never crosses the x-axis, so it's either always above or always below. How did you decide that it was always above? Nice. It is upwards opening and the constant is positive. In fact, either one of those would do the trick. The constant term is positive. That means it goes through 0, 12. So whatever the graph looks like, it has to stay above the x-axis. On the other hand, it's upward opening. If it ever dipped below the x-axis, it would have to hit it twice. But you know it doesn't. So the vortex has to be above the x-axis. All right, so by looking at the graph, which we sketched by hand, I don't know that the vortex is in the right place, and I don't care. This is always above the x-axis. All right, so since this thing is always above the x-axis, what is the solution to this inequality is bigger than or equal to 0? Yeah. All real numbers negative infinity to infinity. Take your pick. Both count. If you're solving it in WebWalk, then pay attention to what answer WebWalk expects. So this one has solution negative infinity to infinity. And you know what? How much time do I have? I have 2 minutes. If I want to change this back to less than or equal to, how would that change what we did? Or I guess even just how would that change the final answer? no solutions. And I guess on the one hand, that's intuitive, like, if this thing is always positive, then it's definitely never negative. On the other hand, like, if you read it off from the graph, the process would be the same. So with my remaining minute, here is what I want to do. There are obviously some examples I'm not going to get to today. We'll do some of them tomorrow. The thing I want to point out is on this next page is like a decision tree for how to solve a degree 2 polynomial equation. And you should read it from top to bottom. So step 1 is solve equality. Whenever you want to solve inequality, start by solving equality. That tells you the endpoints. After that, well, there are going to be 2 options, 2 solutions, 1 solution, no solutions. In each of those cases, you know the endpoints of the intervals that solve the inequality. Check some sample points about each interval. Use that to decide if that interval solves the inequality. Or look at a graph. Sketch that graph by hand. I guess if you have access to a computer, you can use Desmos. Use that computer now to solve the inequality. Cool. All right. And let's see if anyone has issues with what I've done in terms of the seating chart. Either I did something you didn't do, or you wanted to move and I didn't move you. I apologize. Talk to me at some point by email or in person, and we'll do something about it. Thank you. Thank you. You too.